Assalamu alaikum. This is modern control theory. We are discussing state space representation. This is the second class on state space representation. So first step in state space representation is to select the state vector. So the X that we have said. So first step is selecting the state vector or X. So points to be noted in selecting the state vector. Number one, the minimum number of state variable must be selected. Minimum number of state variable must be selected. And secondly, the component of the state vector, that is state variables, should be linearly independent. State variables should be linearly independent. Okay, so the first point is we already discussed what should be the number of the state variable number, and we said that differential parameter, or in other words, we call this one as a energy storing element. Energy storage element, or order of the system. Order of the differential equation of the system. Okay, so this should be equal to the minimum state variable. Okay, so if the order is second order, if it is a second order differential equation, so definitely 2. Minimum number of the state variable should be 2. So if you take more, then the simple will be complex, and whenever we go for the analysis, it will be difficult for the designers to deal with it. And if it is lesser than whatever the minimum number, then in that case, the problem will be we cannot represent the system properly. So that is why we have to be careful about the number of the state variable. But secondly, whatever we are selecting, there has to be linearly independent of each other. So basically say we have 3 state variable x1, x2, and x3. Out of these 3, if we can represent one as a linear combination of other 2, like if we have x3 equal to 7, x1 plus 3, x2, something like this. So x3 can be expressed as a linear combination of x1 and x2. So we cannot say that x3 is not actually linearly independent of x1 and x2. Okay, this is not the notation, just giving you the example. Okay, similarly, linearly independence actually means that we have derivatives. Okay, so say inductor voltage and current, VL equal to L di L by dt. So one parameter is not linearly related to the another one, rather through a derivative term they are linear. So you can say that VL is linearly independent of IL. Okay, so this is how. Bottom line again, as you can see, while you are selecting the state variable, you have to have those energy storing storage elements or derivative terms that will come into account for your state variable selection. Okay, so next point that we should, let's go to the next article, that is article 3.5. So how can you convert transfer function to state space? So article 3.5, converting transfer function into state space representation. Okay, so while we are trying to convert the transfer function into state space representation, we have to select the state variables. In this case, the state variables are called also phase variables. Okay. Some other choices of state variable is also there, but in this particular case, in the method that we are discussing, we call it phase variable. So other choices of the state variable we'll discuss in chapter 5. Now, if we have nth order differential equation, okay, then what we have to do is we have to take this one and convert it to state space representation. In phase variable form. Okay, so nth order differential equation with one point to be noted is with constant coefficients. Okay, so this is the objective of this article. And now say we have a nth order differential equation, something like this. dny by dt n plus a n minus 1 dn minus 1 by dt n minus 1 y plus a n minus 2 dn minus 2 by dt n minus 2 y goes on to finally a1 dy by dt plus a0 equal to b0 u. U is the input, y is the output. One thing just is there should be y here as well. Okay, so this is a nth order differential equation. Now we have to convert this one into phase variable form, state space representation. And the choice of the state variable is to select the output as a first variable, first state variable. So basically what we are going to do is x1 will basically output y. And this particular choice is known as phase variable choice. Okay, and what about the others? Others will be actually the derivative of the previous one, like x2 will be the derivative of the previous one, that is x1, derivative of the x1, and x3 will be the derivative of the x2. So basically, every new variable will be new or subsequent the state variable will be defined to be the derivative of the previous state variable. So based on this idea, so what will be the x2? X2 will be nothing but dy by dt. So the derivative of the previous one. Then x3 will be the derivative of the previous one, that is d square y by dt square, and it will go up to xn. Okay, so xn will be the derivative of the previous one, so basically dn minus 1 y by d tn minus 1. Now, if we differentiate in the both side of these equations, so in this side as well as in this side, then after differentiating, what we are going to get is differentiation method will lead us x1 dot will equal to dy by dt, x2 dot equal to d square y by dt square, x3 dot will be dqy by dt cube, and finally xn dot will be equal to dny by dtn. Okay, so what you can see here is, as you can see, now if you compare this one, dy by dt is nothing but your x2. So we can write it here, this is x2. And this one is nothing but x3. So x3, and this one has to be, okay. So this one has to be x4. And consecutively, the last one is nothing but, now you have to be careful about the last one. Okay, so we know that what will happen before the last one. Okay, xn minus 1 dot will be equal to xn. What about the last one? The last one will actually come from this derivative. So basically, what we're doing here is you have to be a bit careful about this one. So this is nothing but your a0 x1, and this is your a1 x2, and previous one will be a2 x3. So gradually, actually, this is actually your, if you compare this one and this one, then this is your actually x1 dot, xn dot. Then it will be basically an minus 1, and this is your xn. Okay, an minus 2, xn minus 1. Okay, so also b0. Now, what will happen is, as you can see, all these parameter will be going to the other side. And we'll start from x1, x2, x3 in this way. So what you can write here is something like this. Minus a0 x1 minus a1 x2 minus goes on, ultimately minus an minus 1 xn. Okay, and finally the other side parameter, that is b0 u. Okay, so now if we write this thing in a matrix form, then actually the state equation is complete. Like what we have here is x1 dot, then you have x2 dot, x3 dot goes on, xn minus 1 dot, xn dot. So this is a vector, and now, so this one has to be written in terms of the state variables. Okay, so state variables, that is x1, x2, x3 goes on up to your xn minus 1, xn. Okay, so x1 dot is equal to actually x2. So the first parameter has to be 0, second parameter will be 1. Then also rest of the parameter will be 0. Secondly, x2 dot equal to actually x3. So this will be 0, this will be 1. So this is how it will go. Similarly, this one will be 0, 0, 0, 1. Then it will be going up to like this. Okay. So as you can see, a diagonal 1 will be appearing. So similarly, all these will be 0. Eventually the last one, because xn minus 1 dot will be equal to xn. So last one has to be 1. And now here you will have minus a0, minus a1, minus a2, minus a3 goes up to minus an minus 1. Okay, so this is not yet complete because of the fact that this parameter is still there. So we know that we have to represent something like this, x dot equal to ax plus bu. So this portion is complete. Now we have to just add this one. As you can see, only in the last one you have b0. So rest of them will be basically 0. Only in the last one you have to put 1, and then this, sorry, this will be plus all zeros except the last one, which will be 1, then you multiply it with u. So this is your x dot equal to ax plus bu. So this is your a and this is your b. So we are not yet done. We still have to find out what is our output equation. So output equation is pretty simple because of our choice. We have assumed that y equal to actually x1. So this is our phase variable choice. So to represent in a vector form, what you have to do is just the first one has to be 1, and then rest of them will be 0. And then you have your state variables, x1, x2, x3 goes up to xn minus 1 and xn. So y equal to cx plus du, but there is no u in this case. So this is basically your c and this is your x. Okay, so this is the representation. The differential equation that is being converted into a state space representation in phase variable form. So what is our procedure? So if the transfer function is given, so the procedure is, if transfer function is given, then the transfer function, firstly, the transfer function should be transformed into differential equation. Then the differential, you have to take inverse Laplace transformation on your differential equation. And thirdly, you have to, after converting the differential equation, actually you have to cross multiply. Okay. The method for this one basically is cross multiplication. Cross multiplication. Don't worry, we'll go along with an example, so things will be easier. Then you have to take inverse Laplace transformation on the basically the cross multiplied form, and that will give us with the assumption that zero initial conditions. Okay, and then represent that inverse Laplace transformation in phase variable form. So steps are very simple. So now let's start with one example. Inshallah, things will be easier. So example 3.4. One transfer function is given. So something like is provided like this. That is 24 divided by s cube plus 9s square plus 26s plus 24. This is your RS and this is your CS. So first thing is you have to do the cross multiplication. You need to find out the differential equation. So basically CS by RS is given as this is your G of S, 24 by s cube plus 9 s square plus 26s plus 24. So now if you cross multiply, what we have is CS times s cube plus 9s square plus 26s plus 24 equal to 24 RS. Okay, so just multiply. So basically, CS into S cube is nothing but third derivative of your C of S. So you can write this thing as, if you want to, you can write in derivative form, something like this: d3 by dt3 ct plus, definitely this is apply inverse Laplace transformation. Then you have 9 t square by dt square ct plus 26 d by dt of ct plus 24 ct equal to 24 RT. Or according to the book, as you know, the dot notation. So 3 dot means third derivative plus 9 C2 dot second derivative plus 26 C dot plus 24 C equal to 24. Okay, so this is your differential equation. Now, according to the phase variable choice, we know that we take output, that is C, as our first variable, state variable. So x1 equal to C. Secondly, what we do is x1, x2 equal to C dot, and x3 equal to C double dot. So this is our assumption of our state variable. Now, based on this, what you can write is, because you have to write in terms of x1 dot, x2 dot, x3 dot to find out the state space representation. So x1 dot equal to x2, x2 dot equal to x3, and x3 dot equal to, now you have to be careful here. Basically, if you write in terms of x1 and x2, this is 24x1, this is 26x2, and this is 9x3. So all plus, and then this is your actually x3 dot. Okay, and then you have 24 hours. So all these parameters will be going to the other side. And if you rearrange it, what we are going to get is minus 24x1 minus 26x2 minus 9x3 plus 24r. Okay, so our representation is almost done. So now what you can write is x1 dot, x2 dot, and x3 dot equal to 0, 1, 0, 0, 0, 1, minus 24, minus 26, minus 9, x1, x2, x3, plus 0, 0, 24, r. So this is our matrix A, this is our matrix B. And whatever output is always same, because the phase variable choice means you just taking the first parameter as output. So basically this is your 1, 0, 0. It is always 1, 0, 0, 0, 0. So whatever the thing. So basically you have x1, x2, x3, and it is always true for phase variable form. So this is a representation. Now, if you want to draw the block diagram based on this state space representation, then what we have is 3 parameters actually. We have x3, x1, x2, x3 is a 3 state variable. So x3 dot, then you have x3, then you have x2, then you have x1. So if you do the integration of x3 dot, then you're going to get x3. If you take another integration on x2 dot, x3 dot, then you're going to get x2. And if you get another integration of your x2 dot, then you're going to get x1. This is always true, and according to our choice, x1 is nothing but output. So this is your output yt. Now what about your x3 dot? x3 dot is nothing but this equation. So you have a summing junction, and then you will have something like this. So R24R, so 24, the magnitude box should be there, multiplied with R. So this is your R, and it is plus, so you give the plus sign, then you have 24x1. So, and also minus sign, so keep the minus sign here. 24x1, then you have minus 26x2. 26x2, then you have minus 9x3, so minus 9. So this is your block diagram representation of the system in state space. Okay, so this is a simpler case, and also we have to keep in mind that we assumed a transfer function that doesn't have any numerator, dynamic numerator, only it has a denominator. So in the numerator, we have a constant value, 24. And in the denominator, you have s cube plus 9s square plus 26s plus 24. So there is no dynamic function here. Okay, like s squared, something like this. So now let us look at what happens if you have this dynamic function then what is the changes that happen into your your state space representation as well as in the block diagram representation. For that, we should go for another equation, another block diagram representation. Another example, basically. So before that, say we have something like this, RS equal to, now we have something like this. B2s squared plus B1s plus B0. And in the denominator, you have A cube S cube, A3 S cube plus A2 S squared plus A1s plus A0. So now you have dynamic numerator and as well as dynamic denominator. So we already solved what will happen if you have dynamic denominator. Now what we do is we transform this one into two parts, one with only denominator and if there is any constant. So that can also come, like 24 was there here, but in this particular example, there is no common factor. So we say 1 by A cube, A3 S cube plus A2 S squared plus A1S plus A0. And we know the output of this one is your first, your state variable. And other two state variable, that x2 and x3, those are actually internal to these blocks. So x2, x3 is also there. And then the numerator will be dealt separately. So B2 S squared plus B1S plus B0 equal to, then finally we'll have your output. Okay, so we can easily say that C of S equal to, definitely C of S by X of S equal to B2S squared plus B1S plus B0. So basically output is nothing but, which is our eventually the YS as well, is B2S squared plus B1S plus B0 times XS. So if you take it into the time domain, then YT or CT will be becoming something like this. B2, second derivative of it's 1, d squared by dt squared x1 is B1 d by dt of x1 plus B0 x1. Now, I have to be careful. This is nothing but your x2 and this is nothing but your x3. So you can write something like B2 x3 plus B1 x2 plus B0 x1. So if you rearrange this thing, then you can say that B0 x1 plus B1 x2 plus B2 x3 is your output equation. So your only output equation is changing. So in the state equation, there is no change, but if you have the numerator available in your transfer function, then only the output equation, which was previously only the x1, is not true anymore. So your output equation will be something like this: B0, B1, B2 times x1, x2, x3. Okay, so let us look at the example now. Example 3.5, basically extension of your example 3.4. Example 3.5. So now what they have done is they kept the denominator same. So they made it s cubed plus 9s squared plus 26s plus 24. And in the numerator, they have s squared plus 7s plus 2. Okay, so this is your R of S and this is your C of S. So what we are supposed to do, to keep this exactly same as previous one, if you want, you can just multiply here with 24. In that case, you'll have 24 by s cubed plus 9s squared plus 26. S plus 24 will be the first portion, and the second portion, you will have s squared plus 7s plus 2. This will be your x1. This is your RS, and this is your CS, or eventually it will be Y of S in state space representation. So first thing, we're not changing because it's remaining same. So state equation will be same, and that is x1 dot, x2 dot, and x3 dot. That will remain as it is, 0, 1, 0, 0, 0, 1. And then you have, I think, minus 24, minus 26, minus 9, x1, x2, x3, plus 0, 0, 24R. Now, what is the changes that is coming in your equation? Output equation is ys or cs equal to s squared plus 7s plus 2 into x1s. So we'll just take into the inverse Laplace. So basically yt or ct will be equal to x1 double dot plus 7 x1 dot plus 2 x1. So x1 dot is x2, and x1 double dot is x3. So we can write is x3 plus 7x2 plus 2x1. And now if we rearrange 2x1 plus 7x2 plus x3. If you want to write the output equation, then you can simply write in this way: y equal to 2, 7, 1. Then you have x1, x2, and x3. So this is your C. This is your C, and this is your X. So there is no D involved here as well. Okay, so simple idea. And now, if you know what are the changes you have, the output is changed. Your output is no longer C, whether it is a combination of 2x1, 7x2, and x3. So what will be the change in the block diagram? You can draw a separate block diagram, or you can show it in the same block diagram. That is, your output will not be now simply the x1, rather you will have to make some modification. So what is the modification? Okay. Okay, so let us try to edit this one. Okay, so what we'll have is 2 into x1. So we can have a block here, 2. That will be going to a summing junction. All are additive. So then 7x2. So you can take another one with 7 again. And then you can add it here. And x3. So directly x3. Or if you want, you can give a gain of 1 for uniform representation. So all these three will be summing together to find out your yt. Okay, so this is how this is the modification that is coming. But you have to keep in mind that we have added 24 with the numerator and multiply 24. But if you want to exclude that one, then you have to give a gain of 1 here. Okay, so this is all for today's class. Inshallah, see you in the next class. Assalamu alaikum.